Hello everybody, welcome back to Physics 425. What we've been talking about a lot recently is about systems of fermions at low temperatures, and this was relevant because we wanted to understand the behavior of a system of helium-3 atoms, which are fermions, and so we wanted to understand their behavior in a dilution refrigerator, for example. So I want to shift gears now, and I want to start talking about systems of non-interacting bosons and to try to understand how they behave at low temperature. This is also going to be relevant to us because we haven't yet started talking about in detail the behavior of helium-4 at low temperatures. And the helium-4 atoms are bosons, and so the first step to trying to describe that system is to investigate the chemical potential of bosons at low temperature. And so that's what we're going to start with today. Ultimately, I'd like to be able to understand something about superfluidity in helium-4. And so this is a phenomenon that we've referenced several times already. And what we're going to try to do is to make a connection between Bose-Einstein condensation and superfluidity in liquid helium-4. Okay, so the starting point is just to recall some of the results that we've already used for in the past for even when describing fermions. And so we're going to recall the wave function for a monotonic particle in a 3D box. And so this, for example, would be a cube with sides of length L. I think I'm going to use capital L. Okay, so this wave function is going to depend on the x, y, z coordinates. There's going to be some normalization constant. And then we have boundary conditions that the wave function must vanish at the edges or the sides of this box. And the way that those boundary conditions were enforced was by using these sine functions. And so we're going to have a product of 3 sine functions for the 3 spatial coordinates. And these n factors could be any positive integer. Okay, what we had done is we had taken the argument of the sine functions and we wrote them in a cleaner way. So we would write sine kx times x, and then we had a sine ky times y, and we had sine kz times z, where we defined k to be n pi over L. And so kx would be nx pi over L, ky would be ny pi over L, and so on. The Hamiltonian for a free particle, no potential energy, is just the kinetic energy, and we're going to have h bar squared over 2m times 2 spatial derivatives in the x direction plus 2 spatial derivatives in the y direction plus 2 spatial derivatives in the z direction. And so if we operate with this Hamiltonian on our wave function, we get the kinetic energy of our particle. And when we do that, we get the h bar squared over 2m factor, and then we get k squared, where k squared is going to be kx squared plus ky squared plus kz squared. It's the magnitude of a k vector. Of course, after we operate with our Hamiltonian, we also get the wave function back again. Okay, and so that means, therefore, the energy of state I, so if our wave function represents some state I, the energy of that ith state is h bar squared k squared over 2m. And so what we could do is we could say the energy of a particular state is dependent on the magnitude of the k vector. Okay, where if we had some coordinate system kx, ky, kz, maybe there's some state out here that corresponds to some k vector, and then if we project down into the xy plane, we could find the kx value and the ky value, and then if we go back to here, we'll find the kz value. Okay, good. So what we're going to do today is we're going to look at some of the properties of a non-interacting gas of bosons. So we have a collection of bosons. They don't interact with one another, and so we have a bunch of free particles. So let me remind you of the Bose-Einstein distribution. So we'll use the notation n Bose-Einstein, and I'm going to put a little bar over here, and it was written as the exponential of the energy minus the chemical potential over kBt minus 1. So if you remember, the Fermi-Dirac distribution looked the same, but instead of a minus 1 in the denominator, we had a plus 1. What this distribution function tells us is the average number of bosons in a state K with energy epsilon of K. Okay, good. So the ground state of our boson system corresponds to all of the n values equal to 1. And if you go back and look at this energy here, K is, where did we find? N pi over L. So for n equals 1, all of the K values are going to be pi over L. And so, we would have epsilon prime for the ground state energy. So I'm going to use prime for the ground state energy. Ground state energy is going to be h bar squared pi squared over, h bar squared over 2m, and then it's k squared. And so we get kx squared plus ky squared plus kz squared. But for kx, we're going to get pi over L because n equals 1. And then for ky, we're also going to get pi over L, and for kz, we get pi over L. So overall, we're going to have 3 h bar squared pi squared over 2m L squared. And so that's our ground state energy. What we're going to do is we're going to say that the value of the ground state energy isn't physically important. We're only going to focus on the difference in energy between the different states. So the value of the ground state energy is not physically important. Only differences in energy matter. And so what we'll do is we'll shift the energy of our states by this ground state energy. We'll subtract off epsilon prime. And so if we do that, then the energy of state K is going to be h bar squared pi squared over 2ml squared. And then we'll have nx squared plus ny squared plus nz squared. And then we're going to subtract off epsilon prime. But epsilon prime has all these same prefactors, just with a 3, an additional factor of 3. And so we could write this as h bar squared pi squared over 2ml squared, nx squared plus ny squared plus nz squared minus 3. And so now the ground state energy is, say, epsilon 0 is equal to 0 after we've done this shift. Okay, so what we want to think about now is try to write down an expression for the total number of bosons in our system. And we said that the Bose-Einstein distribution was going to tell us the average number of particles in each state. So if we sum over all of the states, then we get the average number of particles in every state in our system, and we add them all up, and that would be the total number of particles. Okay, so the total number of bosons, in the system is, so we're going to take the sum over all quantum states each state in our system is represented by a k vector, so ultimately this is going to be a sum over all possible k vectors. And we're going to evaluate the Bose-Einstein distribution at each one of those states. And so here's our k-space plot again, and our states are represented by points in k-space, and we're going to have a vector, k vector, that represents each one of those possible states. And so I've selected one of them, but what we're going to do is we're going to have to sum over all of these points that populate the entire space. Okay, and so what we have is the sum over k, and the Bose-Einstein distribution is this E of epsilon of k minus mu over kbt minus 1. So we sum over all k vectors. One thing that's important to know is that although this is a sum over all k vectors, the thing we're actually summing over, the Bose-Einstein distribution, doesn't depend on the k vector, it depends only on the magnitude of k. And so that's going to be important in just a second. Okay, so what this really means is that the total number of particles is going to be 1 over the energy of particles in the ground state, so epsilon 0. So it's going to be E epsilon 0 minus mu over kBt minus 1 plus, if we had a k vector k1, then we would have the energy of that state epsilon 1 minus mu over kBt, and then we'd have a k vector k2, and so it would be E over epsilon 2 minus mu over kBt minus 1, and then we keep going on and on and on and on again. However, what we've done is we've shifted the energies of our system so that the ground state has 0 energy. So that first term just becomes 1 over e to the minus mu over kBt minus 1. And then nothing happens with these other terms. Plus and so on. Okay, so what this first term tells us is this is the ground state, and what we have is the average number of particles in the ground state. Average number of particles in the ground state. And then all these other states correspond to excited states, and so this is the average number of particles in the state with k vector k1 and energy epsilon 1. This is the average number of particles in state with k vector 2 and energy epsilon 2, and so on and so on. What we could do is let's look at this first term. So let's examine this average number of particles in the ground state and see if we can learn something about the chemical potential of this system of bosons. So if mu was positive, then we would have e to the minus mu over kBt, so e to the minus positive number. And that would mean that this epsilon term would be less than 1. Then e to the minus mu over kBt would be less than 1. And that would mean that 1 over e to the minus mu over kBt. So we would have 1 over a positive number less than 1 minus 1. And so we'd have 1 over a negative number, and that would be overall a negative quantity. But that doesn't make any physical sense. We can't have on average a negative number of particles occupying any state. So n0 less than 0 is unphysical. We can't have a negative number of particles in a state. And so that means that it must not be true that mu is positive. So in fact, what we require is mu has to be negative. Okay, so that's the first little bit of insight. The next question is, what happens to these average number of particles in the various states as T goes to 0. And so the question is, we don't really know, because if I wanted to answer that question, here they are, I'd have to know what is the temperature dependence of mu so that I could understand what happens to mu over kBt in the low temperature limit. So to answer this question, we need to know the temperature dependence. Of mu so that we can evaluate mu over kBt in the exponential. Okay, so for the remainder of this video, what we're going to be preoccupied with is trying to determine the temperature dependence of mu. Okay, so the first step is, let's say, first we will turn the sum over k in our expression for n into a sum over the magnitude of the k vector, or just a sum over k without the vector symbol. Then we will transform the sum into an integral over k. All right, so what we're going to do is we're going to try to manipulate this expression here. And step one will be to take the sum over vector k and convert it into a sum over the magnitude of k, and then we'll try to convert that into an integral. And actually some of the methods that we're going to use to do that will be familiar from previous work that we've done. So let's consider the sum over vector k of any function of the magnitude of k. This is any function of the magnitude of k. So, for example, it could be the energy of the states, which are proportional to k squared, or it could be, as it is in our case, a sum over the Bose-Einstein distribution, which is also just a function of the magnitude of k. Okay, so for example, let's look in 2D. And so this is the part that is going to be somewhat familiar. In 2D, we would just have kx and ky, and then we'd have our various states. These are the ky equals 1 states with kx equals 1, 2, 3, 4, 5. These are the ky equals 2 states. And then we just keep going. And so we could populate this first quadrant of our 2D k space with all of the various k states. Okay, and then what we could do is we could make a ring in that first quadrant, and we could say all of the k states inside this ring are the same distance from the origin, so they have the same magnitude of k vector, so that they contribute equally to the sum. All of the states inside of this ring make the same contribution to the sum that involves some function that's just the magnitude of k. Okay, and so we'll give our ring some width that is delta k. And we'll also remind ourselves that each k state occupies a certain area of k space. So each k state occupies an area in k space equal to, remember it was pi over L was the spacing between states, and so this 2D area is pi over L squared. And then we also have the area of our ring, which is determined by the circumference times the width. And so our ring of constant k has area of, so the circumference of the ring would be 2 pi k, and its width is delta k. So if it was a full ring, that would be the area, but we have only the first quadrant. All right, and so in our sum, we're going to lump together all of the states that have the same magnitude of k, and so we just want to know how many states are inside that ring. Well, if we know the ring area and we know the space occupied by each state, we can take the ratio of 2 to find the number of states inside the ring. So the number of states in the ring is, well, let's see, we have 2 pi k delta k over 4, and then divided by pi over L squared. And if you work out all the factors properly, we get an L squared k delta k divided by 2 pi. Okay, so I want to generalize this for 3D, and so we'll make a table, 2D and 3D. And so in 2D, the area occupied by a k state was pi over L squared. In 3D, the volume occupied by a k state would be pi over L cubed. The area of our ring in 2D was pi k delta k over 2. The volume of a shell in 3D would be 4/3 pi, it would be the surface area of a sphere, 4 pi k squared times the thickness of the shell, so delta k, and then we would have to divide by 8 because we'd only be in the positive quadrant. So it would be 4 pi k squared delta k divided by 8, which would be pi k squared delta k over 2. And then the number of states, we could say the number of states q in the ring would be the ratio of a ring divided by ak, and it was L squared k delta k over 2 pi. And the number of states in our shell would be v shell divided by vk, and that would come out to be L cubed k squared delta k over 2 pi squared. Okay, so now what we want to do is we want to say, well, what we could do is we could take a sum over vector k of some function of the magnitude of k and say that that's equivalent to, not summing over every single vector k, but let's just sum over now the magnitudes of k, and f of k is going to make the same contribution for all of the vectors that have the same magnitude, and the number of those vectors that have the same magnitude is given by the number of states, this Q shell that we had. And so this is the number of states in shell of radius k and thickness delta k. Okay, I've written this as V, and so V is defined to be this L cubed. It's the volume of our system. And so this is a sum over vector k, and this is the sum over the magnitude of the k vectors. Okay, good. So we can apply this then to the sum that we've constructed to count the number of bosons in our system. So originally we had a sum over vector k of the Bose-Einstein distribution. So we're going to get some prefactors. We have the volume over 2 pi squared. And now we're going to have a sum over just the magnitude of k. And what we get is a k squared delta k. And then we just have to enter in our Bose-Einstein distribution function, which was 1 over e epsilon k minus mu over kbt minus 1. Okay, so that's the conversion to a sum over the magnitude of k. Going to an integral is straightforward, because what we're going to do is we're going to say, well, this process, this manipulation that we've done is valid only when delta k is really small. The thickness of our spherical shell is really, really thin. And so in the limit that delta k goes to 0, the sum just becomes an integral. So in the limit that delta k goes to 0, we have, say, the sum over the magnitude of k of some f prime of k delta k is going to be equal to the integral of f prime of k dk. I put it in f prime because our function of k got modified because we picked up a k squared from counting the number of states in our shell. Okay, so that means then the number of bosons in our system is equal to v over 2 pi squared. The integral k goes 0 to infinity. We need to get all k states, and so we have to consider k vectors of all magnitudes. And then we have a k squared dk over e epsilon k minus mu over kbt minus 1, which is the conversion to the integral that we wanted, and it's an integral over the magnitude of k. All I'm going to do next is separate the exponential in the denominator. So this is k squared dk over e. So epsilon of k is h bar squared k squared over 2m. So we have an e to the h bar squared k squared over 2m kbt. And then we have an e to the minus mu over kbt, e to the minus mu over kbt, and then we have a minus 1. All right, so this is the integral that we're ultimately going to want to do some kind of evaluation of. So we're going to make a substitution, and the substitution is going to be x squared is equal to h bar squared k squared over 2m kbt. So that first exponential in the denominator will just be e to the x squared. And let's see, in the numerator we have a dk, so k is going to be equal to the square root of 2m kbt over h bar squared, and then it's going to be a times x, and so that means the dk in our denominator will be root 2m kbt over h bar squared dx. The limits of the integral when k is equal to 0, x is equal to 0, so that's fine. When k is infinity, x is infinity. So the limits of the integral don't change. Okay, so let's see. N is going to be equal to v over 2 pi squared. When we put in k squared in the numerator, we're going to write that as 2m kbt over h bar squared x squared. So we'll get a 2m kbt h bar squared. And then we'll have the integral from 0 to infinity of x squared. dk is going to become dx, but we're going to pick up a square root 2m kbt over h bar squared. So we already have one factor of that, so when we have the square root, we'll end up with 3/2, and then a dx. And in the denominator, we have e to the x squared. And then we're going to have e to the, I'm going to write it as minus eta, and then minus 1, where eta is defined to be mu over kbt. Okay, good. So then what we've got is, let's see, did I forget something? No, I think that's okay. So what I'm going to do is I'm going to isolate this integral on the right-hand side. So we'll get a 2 pi squared, then we're going to get an n over v, and we'll have a h bar squared over 2m kbt to the 3/2 is equal to integral 0 to infinity x squared over dx, x squared dx, e to the x squared minus eta, if I recombine the exponentials, minus 1. And so finally what we could do is we can say this n over v is the particle number density. So this is the number density of the bosons in our system, the number of particles per unit volume. So then 2 pi squared n h bar squared over 2m kbt to the 3/2 is equal to integral 0 to infinity x squared dx, e to the x squared minus eta minus 1. So this was one of the results that I wanted to get to. And what we're going to do is, remember we said one of our goals was to find the temperature dependence of the chemical potential. So we're going to use this expression that we've just derived to determine first the temperature dependence of eta Now, and because eta is equal to mu, the chemical potential, over kBt, once we know the temperature dependence of eta, if we multiply by kBt, we'll get the temperature dependence of the chemical potential. So we're going to use this expression to determine the temperature dependence of eta, which is mu over kBt. How are we going to do that? Well, if we look at the left-hand side, we have a bunch of constants and then one factor of temperature to the 3/2 power in the denominator, right? H bar squared, kb, 2, and pi squared, those are all constants. If we have a particular system of bosons, then we'll know the mass of those particles, and so that will be a constant. And for a particular system, we are going to know, if we know the number of particles in our system and the size of our system, then we'll know the particle density, n. And so on the right-hand side, we have a bunch of constants divided by t to the 3/2 power. And so we can evaluate the left-hand side. We can evaluate the left-hand side for, a bunch of different temperatures. And so we'll know what that's equal to. On the right-hand side, we have an integral over x. So when we evaluate the integral, there's no x dependence left, right? X varies from 0 to infinity because of the integration limits. And the only other thing that's in there is eta. So what we're going to do is we're going to pick a value of t. We'll evaluate the left-hand side. And then on the right-hand side, we'll pick a value of eta and evaluate the integral. And if the left-hand side and the right-hand side are equal, then we know eta at that particular temperature. If they're not equal, what we'll do is we'll keep adjusting eta until we can make the left and right-hand sides equal to each other. Once we've done that for one temperature, we pick a new temperature and we start over again. Okay, so for example, for liquid helium-4, we can just look up the number density of helium atoms in liquid helium, and it's 2.2 times 10 to the 28 per cubic meter, and the mass of the helium atom is just the 4 nucleons, 2 protons and 2 neutrons, and that comes out to be 6.68 times 10 to the minus 27 kilograms. And if you put those numbers in, then the left-hand side of our equation can be written as 3.42 Kelvin divided by T to the 3/2 power is just equal to that integral that we have. So nothing changes on the right-hand side. Okay, so the process is, one, is to pick a temperature T. And then we evaluate, say, the left-hand side of our equation. Then we adjust eta until the right-hand side is equal to the left-hand side. So every time we pick eta, we have to actually evaluate that integral. And it's not an easy integral to evaluate, so we do it numerically. So the integral is evaluated numerically. And you could use whatever you want to do that. Maple, MATLAB, Python, it doesn't matter. So once we've done that, once we've satisfied left-hand side equals right-hand side, then we now know eta at that temperature. And we can also calculate mu, the chemical potential, is kBt times eta. Okay, and then what we do is we repeat for a new temperature. And we can do this over and over and over and over again, and we can construct a table, and that table is going to be T, the left-hand side of our expression, then we adjust eta until we get left-hand side equal to right-hand side, and then we can calculate mu. So we start with T1, the left-hand side is going to be 3.42 Kelvin, divided by T1 to the 3/2 power, and we find the right value of eta, eta1, and then we calculate mu1 is kBt, eta1. And then we get a new temperature, T2, and we start all over again. Okay, and then you keep going for as many values as you want. Okay, and so I've done this, and I wanted to show you some of the plots that came out of this. And so here is on the horizontal axis is temperature, and it goes from about 1 Kelvin to 100 Kelvin. And then on the vertical axis is the value of eta. So these are the eta values that I've had to adjust in the integral in order to make left-hand side equal to right-hand side. And what we're interested in is the fact that, so I think what we could do is, let's see, if I was to try to draw a straight line, let me see if I can draw a roughly straight line here, starting from the high temperature side. What we can see is that as we get to lower and lower temperatures, the calculated values of eta are starting to deviate from this straight line. And in fact, what they're starting to do is they're starting to curve towards 0. And so at low temperature, this eta, which is mu over kBt, which appears in our Bose-Einstein distribution function and the average number of particles in the ground state in state with energy epsilon 1, states with energy epsilon 2. And what we were worried about is what happens when we go to the very low temperature limit. Well, it looks like that ratio of mu over kBt starts to go to 0. In fact, if we fill in these points, the blue line is the filled in points between all of these values. And if you could extend it, it would approach 0. Okay, if we multiply this eta by temperature, then we get the temperature dependence of the chemical potential, and that is this red data. And then you can see the chemical potential, as we said, would be the case. It's always negative, so that we don't get less than 0 particles in the ground state. And you can see clearly here that it's starting to curve towards 0. Okay, good. So what I want to do is just make a couple more comments about this, and then we'll wrap it up for today. So let's go back to our notes, and what we find is, so this analysis shows that eta, which is equal to mu over kBt, goes to 0 as t goes to 0. So the average number of particles in the ground state, if you recall, or if you look back, was given by e to the minus mu over kBt minus 1. There's no epsilon because we set the ground state energy to be 0. But if mu over kBt is going to 0, what we have is e to the 0 minus 1, which is like 1 minus 1. And so we have 1 over 0. So that means we have a huge number of particles going into the ground state when t goes to 0. And so that's, I think, naively what you would have expected for bosons, right? Because all the bosons are allowed to go into, like, there's no exclusion principle. You can have as many particles as you want in any state. And at the lowest temperatures, all of the particles start to occupy the lowest energy level. Okay, so on the other hand, say the average number of particles in state X, where X could be, say, the 1, 2, 3, or whatever, right? Not the ground state. So what was Nx equal to? It was 1 over e to the epsilon x over kBt at e to the minus mu over kBt minus 1. Okay, but this is going to go to, if mu over t goes to 0 when t goes to 0, then this factor just goes to 1 at the low temperatures. And so this becomes e to the epsilon x over kBt minus 1 as t goes to 0. But all these energies are states that are above the ground state, and so epsilon x is positive. Epsilon x is positive, right? There, it's above the ground state energy. And so therefore, e to a positive number divided by kBt, but t is going to 0, so we have a positive number divided by 0, so we have some huge number in this exponential, and so this becomes huge as t goes to 0. And so therefore, Nx is 1 over a huge number minus 1. So the minus 1 doesn't matter, so we just have a 1 over a huge number, and so this goes to 0. And so what we find, of course, for a system of bosons is that as we start to approach low temperatures, we start having all the particles vacate the higher energy states and converge into the lowest energy state. Okay, so next time what we're going to do is we're going to start to talk about Bose-Einstein condensation. Bose-Einstein condensation. And the goal will be to try to quantify when do we have, at what temperature do we have all of our particles suddenly occupying the ground state. We know that that's going to happen for t equals 0, but is there some kind of critical transition temperature that we can define that characterizes when our system makes a sudden transition to having a huge number of particles in the ground state? Okay, and so that's where we'll leave it for today. Thank you very much, and we'll see you next time.